Hello and welcome to another Arlington High School Math 4 Honors lesson. My name is Kirk Weiler, and today we're going to be doing Unit 11, Lesson Number 9, Antiderivatives and Differential Equations. This is the last lesson in this particular unit, Unit 11. We have only one unit left after this. It's a short one on multivariable relationships and functions. I'm very excited to move on to that. But today we're going to be seeing how the antiderivatives that we worked with in the last two lessons can be used to solve what are known as differential equations. So before we do that, we may want to talk about what is a differential equation and what in the world does it mean to solve it. Alright, so differential equation is an equation that contains a derivative. That's it, right? An equation that contains a derivative. So those three equations that just popped up on the screen, they're three cases of differential equations. This is a differential equation because obviously it's an equation and it involves this first derivative, dy dx. Here we've got a differential equation that involves a couple derivatives, this second derivative and this first derivative. Here we have an amazingly simple differential equation. Now, what does it mean to solve a differential equation? Well, real quick, let's talk about what it means to solve an ordinary equation. We all know that the answer to this equation is x equals 5. All right. But the reason that it's a solution because x equals 5 makes this thing true. Makes this equation true. In other words, if I substituted 5 into this equation for x, we'd get 11 equals 11, right? Likewise, the reason that x equals 7 is not a solution is because it would make the equation false, right? When we substitute that in, we'd get 15 equals 11, and that's false, so it's not a solution. That's simple enough. So what does it actually mean then for, what does it actually mean for us to solve a differential equation? Well, we're going to find, y equals f of x, some function that makes the equation true. So no different than when we solve a normal equation. Well, a little different, but it's the same idea. Now, before we get into this, I wanted to pause just for a minute. Differential equations are huge. In fact, one might claim that even sort of any field of engineering or science, differential equations are the name of the game, so to speak. They are the next level of calculus. Once you get done with the traditional first, second, and third semester calc sequence, you oftentimes take a differential equations course. Sometimes you even take it concurrently with third semester calculus. In physics and engineering, it's really all about modeling physical processes using differential equations and then solving them. Some differential equations are extremely difficult to solve, and there are entire math courses devoted to solving differential equations with different techniques. We're going to look at an amazingly simple type of differential equation today, and one that has an easy technique for solution. Anyway, I'm going to clear this out. So, how do we solve a differential equation? Well, apparently we already did that. Anyway, today what we're going to be doing is we're going to be looking at differential equations that kind of look like this. dy dx is some function of x. Okay? That doesn't have to be the case. There could be y's, x's over here, there could be a second derivative here, but today this is all we're doing. So when I look at this particular differential equation, dy dx equals 10 minus x, I want to solve it. I want to find a function that makes that true, but subject to the condition that y equals negative 1 when x is 0. Pause the video for a minute right now and think about how we might do this. Hopefully, the word antiderivative came to your mind, right? In fact, I mean, if I want to find a function that has this as its derivative, in fact, right, I should probably just find the antiderivative, right? I know then that the derivative of this will be this, so that's all good. Now, what's wrong at this point is that this doesn't work. If I plug 0 in here, I don't get negative 1. That's where that plus c comes in, although now it is not arbitrary. In fact, we need to solve for it based on that condition. That's pretty easy, right? I put negative in for 1 in for y, 0 in for x, because we're dealing with a very nice polynomial. This is very easy. C ends up being that negative 1. So our final answer is simple enough, is 10x minus 1/2 x squared minus 1. That's it. Really, there's nothing more than that today. In fact, that's more or less the whole lesson. So we're going to get a lot of practice. We're going to go through this quickly, and we're going to finish up this unit. I'd like you to pause the video and work through letter B. Try to do this entire problem without your calculator, okay? All right, let's work through it. We need to find an antiderivative for this. Now, you just spent 2 lessons coming up with antiderivatives, although the last one, if you're working through my curriculum, was on reversing the chain rule. This one I don't need to have any kind of chain rule reverse on it, but what I do need to do is bump that 1/2 power up, right? And it's going to go to the 3/2, but then I'll have to multiply by 2/3. Conveniently, we get some 3's to cancel, and I'm left with y equals 2x to the 3/2 plus c. Now I have to solve for c, so I'm going to put in 4 for y, and I'm going to put 9 in for x. Now here's the reason I told you to do as much of this by hand. The AP exam certainly expects students, and so do colleges, they expect them to have some fluency with easy, small, fractional exponents, right? You shouldn't need to do 9 to the 3/2 on your calculator. You should be able to say, oh, 9 to the 3/2, well, that's just the square root of 9. That's then being cubed. It's also 9 cubed, then take the square root, but it's easier to do it this way, right? So 9 to the 3/2 is 27. Now don't forget that 2 sitting out front, but the rest of it is some pretty easy algebra. And in fact, c is negative 50, and our formula is 2x to the 3/2 minus 50. These may not be as easy to check as antiderivatives, but they're pretty simple, right? You need to make sure that the derivative is correct, and you need to make sure that whatever initial point the curve actually goes through. But those are all within the skill set of a student at this point in this course. All right, I'm going to clear out the text, then we're going to do some more. So copy down what you need to. All right, here we go. Next page. Find a function f such that f prime is negative 6 sine 2x and f of 0 is 10. Pause the video again and see if you can find this function. All right, let's do it. Well, we'll guess and check here. I know that if this is the derivative, then my antiderivative must involve a cosine 2x plus c. Question is that right? Well, if I took the derivative of cosine, I'd get negative sine, and it would be 2x, and then I'd multiply by 2. So let's compare. Looks pretty good, but I need a negative 6, and all I have is a negative 2. I think if I put a positive 3 there, it would get the job right, because negative 1, 2, 3 gives me negative 6. Great, I'm going to get rid of this, just to give myself a little space to write. Now, of course, I can solve. I'll put 10 in for f of x. I'll put 0 in for x. Now, be careful here. Cosine of 0 is equal to 1. So I get 10 equals 3 plus c. c is 7. So my final answer, f of x, equals 3 times the cosine of 2x plus 7. Some students pick up a worrying habit where they just kind of assume that that's the plus c. Clearly it doesn't have to be. It wasn't in the last exercise, it wasn't in this one, so be careful. Unless you're very, very confident, only use that as your plus c if you know it's right. All right, I'm going to clear out the text. Here it goes. All right, let's jump and do another one. A function y equals g of x exists such that g prime of x is 8x e to the x squared. If the y-intercept of g is 2, then find a formula for g of x. Again, pause the video now, see if you can work through this. All right, let's take a look. Now this really comes from our last lesson because this is definitely a derivative that came from the chain rule. Came from chain rule. All right. Now, there is no way to get an e to the x squared in a derivative unless we start with an e to the x squared. I shouldn't say there's no way, but it's very unlikely. So that's going to be my initial guess. Then I'm going to take its derivative. The derivative of e to the whatever is e to the whatever, but then I'll have to multiply by 2x. So do the comparison. Everything looks good except for the 2. That's a good thing. So I just need a 4 there to turn that thing into an 8. All right, now we have to solve for c. So we'll do 4e to the y-intercept. Y-intercept of g is 2. That means the point 0, 2 lies on it, right? Yeah. So what do I have? I've got 4e to the x squared, 0, plus c is equal to 2. E to the 0 is 1, and that's going to let me solve for c, which is negative 2. So g of x, 4e to the x squared minus 2. All right. And again, pretty easy to check. Pretty easy to check if you're confident with your derivative work. All right, I'm getting it cleared out. All right, let's take a look at another motion problem. It says, find an object's velocity, v, and position, x, as functions of time if its acceleration is given by a of t equals negative 4 sine 2t, and v is 4 and x is 5 when t is 0. So we're really coming up with two functions now, a function for v of t and a function for x of t. Why don't you pause the video and go ahead and do that. All right, let's start by writing down this statement. v prime of t is negative 4 sine 2t. So v of t, its antiderivative, well, let's see, what would we have? We'd have cosine of 2t. If I took the derivative, I get the negative, but then I'd only have a 2. So something like that. Right? That's right. I take the derivative, introduces the negative, multiply 2, it gives me the 4. Yep, it's all good. Let's solve for c1. Let's put 4 in for v. Let's put 0 in for t. Got to watch out here. Cosine of 0 is again 1, so I'll get c1 plus 2 is 4, so c1 is 2. The reason I use c1 and not just c is I'm going to have another constant. So I want to distinguish between the two. Boy, there's a lot of 2's floating around here, aren't there? V of t is 2 cosine 2t plus 2. Now, x of t, well, this thing is x prime of t. So x of t, we're going to just do it again. So let's take a look. I have to find a derivative and have cosine 2t. I'll start, I think, with sine 2t. Let's see, take the derivative of sine, I get cosine of 2t, then I multiply by 2, 2. That's it. Now I have to be careful, though. I have to find something whose derivative is 2, and that's going to be 2t. Right? Number one error is forgetting that. Let's keep going. Put 5 in. I have sine of 0 plus 2 times 0 plus c2. These are gone, so c2 is 5. So my position formula is sine of 2t plus 2t plus 5. All right, and that's that. Right, nice little motion problem. We did something like that similarly earlier in the course. Didn't have so many sines and cosines in it, but something similar. All right, I'm going to clear this out, so copy down what you need to. All right, last problem. This was, I have to admit, kind of taken off of an AP multiple choice question, but I love the way that it was worded, so I wanted to expose you all to it. It says, for every point xy on a given curve, the slope of the curve is given by 2x plus 1. If the curve passes through the point 1, negative 2, then find a formula for y. Well, it's kind of cool. Because here, when they say that the slope is always given by 2x plus 1, what they're saying is that dy dx is 2x plus 1, right? Therefore, y, well, that would have to be x squared plus x plus c, right? We can now find that plus c by substituting in negative 2 for y, 1 in for x. So I'll get negative 2 is 2 plus c, and c is negative 4. So y is equal to x squared plus x minus 4. Again, easy enough to check that its derivative is 2x plus 1, and easy enough to check that it goes to the point 1, negative 2. All right, those are antiderivatives combined with differential equations. There's a lot more of that story to be told, but it's as far as we're going to take it in this course. I'll clear out the text, copy down anything you need to. All right, here it goes. Okay, well that was Unit 11, during which we looked at major derivative theorems. We looked a little bit at max-min problems. We looked a lot at optimizing. Then we got into antiderivatives and finally their applications with differential equations. All right. We have one more unit to go, Unit 12, which is going to be on multivariable functions and relationships. I love that one, but it's a very short unit. And then we are done with Math 4 Honors for the year. At least, you know, the non-review portion. All right. For now, though, let me remind you that this has been another Arlington High School Math 4 Honors lesson. My name is Kirk Weiler, and until next time, keep thinking, keep solving problems.